All right, so I should have those exams graded later today. Don't know if I'll get them posted before I leave today, but for sure tomorrow I'll probably get them posted and I'll hand them back on Wednesday. So I can't really speak to them. I haven't really gotten through enough of them to where I have an idea about what the average was or anything like that. But we'll talk a little bit more about them Wednesday. Once I get them graded and handed back, I'll kind of post the exam and the answer key up on Canvas. So you can go back through, the ones you missed, you can kind of figure out what you did wrong or what the right answer was. If you have any questions, feel free to reach out once that occurs. Other than that, once I get those posted, I'll get kind of the grades, that should be pretty up to date and reflective on Canvas once those exams are uploaded. And I get those, the next Excel assignments graded as well. So probably by the end of the week, you should have a pretty good idea of where you stand at in the class once the exam scores are factored in and once those second Excel and Connect assignments are factored in as well. Okay. Any questions for me before we jump into new material today? How was the exam? Not too bad. Really bad. I guess I'll get an idea next 24 hours. So we're gonna kind of, each one of our exams is completely separate from the other, and so we're gonna start like a whole new batch of material. It's gonna be a little bit different than what we kind of did in the first half. I'd say that the variety of topics is a little bit more, not as wide, right? So we're gonna be really focusing in on like one main topic, which is the normal distribution and sampling. Right now, before we get there, we'll kind of have to do a little bit today where we set things up. And I'll put a smart book assignment up after class that just kind of has, it's not an assignment, but the practice kind of, if you want to kind of go through the material that we're about to cover, it'll kind of prime your mind or just kind of review of what we're talking about in class, seeing it a different way. But we're going to start talking about continuous random variables. So before we were doing discrete, right? Binomial, Poisson, we can only see 0, 1, 2, 3 successes, right? But think about a truly continuous random variable. This is where we can see, it doesn't have to be 0, 1, or 2, it could be 3.59, right? So we get a much wider range of possible outcomes we can now see for this random variable x, right? We're still dealing with random variables. So we talked about examples of this. We can still get kind of a nice probability distribution for these continuous variables. So before, with the discrete ones, right, we had like basically a bar, right? The probability that we saw 0 successes, the probability we saw 1, probability saw, but we kind of get this idea of what the distribution looked like. With a continuous random variable, we're going to get more continuous lines. So it's not just the bars, it's going to be a nice kind of like functional form. Right? Another thing I want to think about here is kind of set this up, and we'll talk about this a little more later on. So we're still going to be thinking about, I guess, if we had our y-axis, we're still thinking about that y-axis is telling us the probability of these different outcomes we could see for x. The only difference is now it's not just a bar at 0 and 1, it's every single thing in between. So it looks a little bit like calculus. Don't worry with what we do in calculus. But the idea is like, if I could find the probability, I don't know, x is equal to 2, I could draw a line up to whatever that probability is. And then I could, okay, what if it was equal to 2.01? Draw a line up there. What if it was equal to 2. I'd have like all these infinitesimally small kind of bars. It's just that there's, I went from 2 to 2.01. There's technically how many values in between 2 and 2.01? Anybody else YouTube spiral about infinity, right? So like we get between any two numbers, there's an infinite number of possible numbers. So we truly are going to have like an infinite number of kind of these bars underneath this nice continuous kind of line that we have. Right? So we usually won't draw those bars out. We just kind of display it using this nice line. Right? Now the issue becomes, it's a little bit weird, and we'll start out today with a very unique continuous random variable, which is the uniform, which means everything is equally as likely. It's not the most realistic and out in the real world, but we see it, occasionally happen. So let's say we go back, and if I'm flipping a coin, we said we had how many outcomes? 2, heads or tails? What was the probability of either one? 1 over 2. And if we roll the dice, 1 over 6, right? We said the general rule, if everything's equally as likely, right? We had that like classical assignment of probabilities. It's 1 over the number of possible outcomes that we have. Right? Well, even between 2 and 2.01, if there's an infinite number of numbers there, for a truly continuous random variable, my number of outcomes is infinite. Right? Anybody, I don't know every class, the math background exactly, but what is this? What would you say 1 over infinity is? Close. So if we have 1 over infinity, we can actually kind of do this mathematical proof to show that in the limit it approaches 0, right? So the idea is like if I have an infinite number of possible numbers, the probability that I get any one of those numbers is actually 0. It's this real weird kind of mind something that like it's just hard to envision, right? But if there's an infinite number of numbers, every single number actually has a probability of occurring of 0. However, we know that for something like income, right? Even if I truly could measure that out to whatever decimal, it's going to be way more likely if I chose a person at random, they make somewhere between $40,000 and $50,000 than that they make between $440,000 and $450,000. So we know that there's different values that are more likely, but we can't find the probability of any one specific value. But what we can do is find the probability over an interval, right? So when we're dealing with these continuous random variables, it's going to be a little bit different because we can't find the probability of one specific value. That would just be 0. But it's kind of weird if we looked over an interval or a range of values, we actually can find, oops, what those probabilities are. And what it ends up being is just kind of that area under the curve in between those two values. Like I said, not to give you flashbacks of calculus or anything, but like that's essentially what you're doing in calculus. We're not going to do all that work. We're going to end up seeing that other people have already done that for us. And we have a nice tool to where we don't have to do the calculus every single time. And I'll introduce that on Wednesday. But before I continue here, one thing that I will expect you have kind of moving forward in class, I might be asking you kind of unclear questions or just going to be helpful to have in front of you, is this file down here, which is called z-tables. Okay, so it's going to be our standard normal or z-tables. That's what's going to have all that integration already done for us, so we don't have to worry about using calculus. So I expect, and I can try to put it up on the screen, but it's really small. It's hard for you to see. I just suggest print this out and kind of whatever you bring to class, make sure that's in the folder or in wherever your items are that you bring to class. So kind of expect that you have that. You could also pull it up on your phone since it's on Canvas if that's fine. If that's how you want to do it. I just think it's a little bit easier to kind of have a physical kind of paper. So, any questions on that before we keep going here? And if for whatever reason, usually these PDFs are okay. I feel like sometimes on a Google Chrome, they like will pop up and look odd. So if you pull it up and there's like nothing there, or I don't know, it's like page not found, let me know and I can try to get a different version of the file up there. But I think that a PDF form usually works. It's usually a Word document that has maybe some issues. So we can find the probability over a range of values, over these intervals. Okay. So what we're going to think about is, well, we've still got all these X outcomes. We've got probabilities associated with, even if we wanted to, we could look at really small intervals. We could look at intervals of 0.0001 and still find a probability there. We just can't find the probability of one specific value. So if we looked across every single outcome, right, integrated or looked for the area underneath our probability density function, it's essentially like adding up all these infinitesimally small kind of rectangles. So if we add up the probabilities across every single outcome, just like with discrete random variables, it should always add up to 1. Okay. We add up the probability over the entire range of possible values we can see for X, that should equal 1. It's like what we had with our discrete. We know that the probability over an interval has to be at the very lowest 0, right? We can't have negative probabilities. So we've got it's going to be greater than or equal to 0 for any interval that we're looking for. But visually, I'll start drawing out what we end up, I'll kind of introduce this more on Wednesday, but a normal distribution. You can think about the area under the curve, right? Or under this line is essentially 1. What does that represent? Very similar when we had those Venn diagrams. The area of 1 is our experimental outcome space. And then what are the different outcomes we can see? All the X values in that range. Okay. So the area in this curve is 1. Today, we'll deal with the one that was a little bit different, but for now, we'll kind of keep this idea of using that normal distribution. Is there anything else I want to say here? Because I already have this up here. So yeah, if we look at the area under the curve, this is always going to be one. And we're going to kind of exploit this moving forward. We'll talk a little bit more about that on Wednesday. But for today, we'll focus on a very unique continuous random variable, which is the uniform. So if a random variable, continuous random variable, is uniformly distributed, it means every single outcome or every single interval has the same likelihood of occurring. Okay? So what's that going to look like visually for us? We'll try to preempt this to kind of see how we would run another room. So let's say I've got this continuous random variable x, and I know that it can take on the values between 5 and 15. Okay, so that's kind of like the highest x value I could ever see this variable be. This is the lowest I could ever see that x variable be. But I could see any value in between. I could see 7.39125. Well, if it's a truly uniformly distributed random variable, we know that every single interval of the same size will have the same probability of occurring. You almost think about it like this. If I were to think about what's the probability I see this random variable take on an outcome value between 5 and 6? Well, you could think about it like I could find what that probability is and kind of draw a bar up to whatever value that would be. Well, if I then look at the same interval that goes from 6 to 7, it has the same probability of occurring. That bar would have the same height, right? Have the same probability of occurring over that same interval. And then going from 7 to 8, same probability of occurring, so it would have the same height. So the uniformly distributed variable, we end up with basically just kind of a rectangle. Okay? So it's a very unique case. It's not a normal distribution, but it's a continuous random variable that is symmetric, right? So when we say it's symmetric, that means if I can find the mean, that it would like fold on top of itself. So C and D are just representing that minimum and maximum value that I could see this random variable take. Okay? So C is my minimum, D is the maximum value. Any questions at this point? Shouldn't be too bad. Jump the gun a little bit here. Draw this out. So let's say go from 5 to 15. And you kind of think about it, really, this uniformly distributed variable actually does then also have kind of these legs to it. Basically, if this is the lowest possible value I could ever see, anything below that has a probability of 0. Like I can never see it. Anything above the maximum has a probability of 0. I can never see it. So we can kind of think about here's my maximum, or as we're kind of using the general notation, just D there, and my minimum, we're kind of representing as C. So if I was trying to find the mean of this random variable, right, you had to guess the expected value or the mean, what do you think it would be here? If everything's equally as likely, and the highest value I can see is 15, the lowest I can see is 5, that middle value is going to be 10, right? It's whatever exactly splits that range of values in half, right? Now, if we have more complicated minimum and maximums, it's harder to kind of envision what that is, but really all you're doing there is saying, well, look, if everything's equally as likely, it almost goes back to our regular mean, right? Everything was being weighted by 1 over n. Well, here are a number of outcomes, right? We've got an infinite number of possible outcomes, but every single one would have a weight of 1 over n. Right? So it's as easy as we have the minimum and maximum values. All we're doing is looking for that middle value, right? Or the average of our minimum and our maximum. Because every single outcome has a counterpart, right? If I kind of think about, so we're just looking for that middle value between the minimum and maximum. So for uniformly distributed variable, what should be true about the mean and the median? So what was the definition of the median? That was what exactly split our data, 50% above it, 50% below it. So what's the median of a uniformly distributed variable? The exact same thing, right? It's symmetric. right? So if I fold this on top of itself, that means it's mirroring each other. That means there has to be 50% over here and 50% over here, right? Which we know the mean is going to be that middle value. It just works out for a uniformly distributed variable. The mean is the same as the median. Now we won't really talk about the median very much, but that just kind of to relate to ideas we've already talked about. So what's the height of this uniformly distributed variable going to be? Okay. When you think about when we were doing before, it said if we had n number of possible values here, we said there's truly an infinite number. But we can kind of think about this when I was drawing them out before. It's almost like if I wanted to find the area or the probability of a range of 1 here. So let's say I wanted to find the probability of going from 5 to 6. Right? Well, every single interval of size 1, I know that that would have to have what? A probability of, if I did intervals of size 1, how many of them would fit in between 5 and 15? 10, right? The interval length is 1. That would be 10 of them, right? There's 10. If I take 15 minus 5, that's a range of 10. If I do intervals of size 1, there's how many times is 1 going to 10? 10 times, right? So each one of those intervals of length 1 would have the probability of occurring of 1 over 10, right? Or kind of 1 over however many equally sized intervals of length 1 I could fit in between my minimum and my maximum. So what I'm really doing there is saying the probability of any interval of size 1 will be 1 over whatever the range of my variable is, wherever the distance is between my minimum and my maximum. Okay. So I wrote it kind of up here using the D and C notation, but really all you're doing to find the height of that uniform distribution is 1 over the maximum minus the minimum, or 1 over, what do we call this? Didn't do very much with it, but the range, right? We said it's not the most useful measure of variance, so we then moved, or variation, so we moved on to the variance. But here, right, we can kind of refer to 1 over the maximum minus the minimum, or 1 over the range of possible values. Well, now that we know that, we can actually do some things like, let's say I wanted to find the probability I'm in between 10 and 13. So there is a formula for this, but I think it's an easier thing to have the visual, right? So if I've got the visual, I told you this is a rectangle, right? And I'm looking for the probability that I see something in between 10 and 13. Well, just like when I had that normally distributed variable and I said we could like integrate or look for the area under the curve in between those two values. That's all we're doing here. It's just our curve is a flat line. So really what I'm looking for here is the area of a rectangle. How would you find the area of a rectangle? Base times height, length times width, whatever, whatever we want to call these, right? Well, I just told you how we can always find the height of a uniformly distributed variable. It's just 1 over the range. So here would be what? 1/10 or 1 over 10. What's the length of my interval that I'm looking for? Or what's my base? We're going from 10 to 13, so 3. So the probability I see this random variable x take on a value in between 10 and 13 is, well, this doesn't really look like a 3, but 3/10. Right? That kind of makes sense because there's 10 intervals of length 1 in there. If I've got a range of values I'm interested in that has what? 3 intervals of length 1, well, that would just be 3 out of the 10. Probability of 0.333, or not 0.33, 0.3, sorry. So I can do this with any uniformly distributed variable. I can find the height of that distribution. And then when I want to know the probability I see it take on a value in between a certain range, it's just a matter of finding the area of a rectangle. Right? Now, what that boils down to is actually you can always use this formula, right? So I'll prove it to you with these numbers, but B or A and B are just where my interval that I'm interested in starts and stops. Right? So in this case, if I wouldn't have thought about this as the area of a rectangle, and I use that formula and I plug in, okay, where does my interval start and stop? 13 minus 10 over D minus C, which is just the maximum minus the minimum. So there, 15 minus 5. I end up with the exact same value as if I just treated this as finding the area of a rectangle. whichever way you think is easier, that's fine. If it's just easier for you to know, that's the equation that gives you the probability of being in between two values. By all means, go ahead and use that. I just think for most people, having the visual to go along with it, it's a little bit easier to just think of it as finding the area of a rectangle. Okay. Any questions up to this point before we keep moving here? Okay with this? All right. So one thing I will point out, it gets a little bit tricky with this. If I instead had a negative value for my minimum, I need to be really careful that I remember I'm subtracting that minimum. So like in this case, it would actually be what? 15 minus -5, right? Or it'd be a range of 20. Right? I've kind of widened that interval to be a length of 20. So we're dealing with negative values. You just have to remember you've got kind of two negatives here, kind of mean that you would add whatever that minimum is. Okay. I think that's all. Any other questions up to this point? Trying to anticipate things. So, I already kind of mentioned the mean here, that it really is just finding that middle value in between the minimum and the maximum. Right, so just adding them up, dividing by 2 will give me that mean, ends up being the same as the median. The variance will always follow the same formula as well, right? Now, this doesn't have any, like, there's no intuition, like, I don't think this doesn't really give us any intuitive result here. But you could go through the mathematical proof and think about, if I have this range of possible values, if I took every single X value, subtracted the mean, I have this equation as my mean. I then added that up across every single possible value. If you simplify that formula down, it'll always simplify down to whatever the range of your uniform distributed variable is, so maximum minus minimum, squared divided by 12. Then, why 12? Well, there's like a 2 in here. When we're subtracting, remember, then we take the deviation, we square it, so that, there's some, and then we kind of have, whatever, I didn't write it up here, but B minus A over D minus C, so you can kind of see there's another D minus C or another maximum minus minimum there, and that gets squared. So that's where 12 comes from, is just that, mathematical proof. We don't have to worry about why it is what it is. We can use this equation, right? The variance of a uniformly distributed variable will always be the range of that variable squared divided by 12. And if I want the square root, what's the only other thing I have to do? Or I want the square root. What was I going to ask you? If I want to find the standard deviation, what do? I take the square root, right? So Monday. So same kind of principles are applying. We could never see a non-zero variance. Like, the range of possible values can't be negative, right? The very lowest it could be is 0. So same kind of principles. My variance will always be greater than 0, right? We find the standard deviation the same way as well. So let's work on this one. So we've got kind of this mean, right? I kind of already talked about how we find that. Let's say there's some new movie coming out. Hulk Hogan's career's having a resurgence. And this movie theater wants to know how many pounds of popcorn it would make. And I know that demand is going to be uniform between 1 and 10 pounds. That's going to be, the total amount of pounds of popcorn demanded when they put this movie out. What would the mean of this uniformly distributed variable be? So, kind of help you out. I guess I'll open this up if anybody else is, or if anyone's able to get this ahead of time. Okay. So let's say I wanted to kind of give myself a nice visual where I've got this uniformly distributed variable, and I know that it's somewhere in between 1 and 10. So if I'm looking for the mean, remember, for uniformly distributed variable, that's exactly what would split this in half. So I'll give you a little bit of time. Equations up there, hopefully kind of after seeing the other one, we was using those hypothetical numbers. We've got our minimum and our maximum. So here's my maximum, here's my minimum. All I want you to do is find the mean of this uniformly distributed variable. So I'll give you another 30 seconds or so. This one shouldn't be too bad. All right. You haven't gotten an answer in. Take your best guess here. 32 of us here today. All right. I'm going to close it out. So hopefully this one wasn't too bad. Okay. We did pretty well. So if I'm thinking about, wait. Okay, I was good. I was going to say, was that bar for C? Why does so many people have, why does C make absolutely no sense? I mean, it's outside the range of my possible values. Remember, I'm still looking for a mean. It's the middle point of this variable. Now here, where could I have maybe made some mistakes? Well, I should be using this formula, right? Where I just simply add the minimum and maximum up, divide by 2. So I should get 5.5, right? But why might I have thought 4.5? Well, if I get this confused with when I'm finding the height of the distribution, remember the height of my distribution was 1 over the maximum minus the minimum, right? I was looking at that range. We're not looking at the range of possible values for the mean. We're simply finding that middle value, right? In the middle value in between two numbers is just adding them up and dividing by 2, right? So if I instead had done what? The maximum minus the minimum divided by 2, that's maybe how I could have ended up with 4.5, right? Or if I just try to eyeball this, maybe I just don't think about the numbers right. One thing that would be kind of a nice check if you ever have to calculate the mean, to think about like just a quick check to make sure it makes sense. If I plotted this, right, and I think about I found the wrong answer, let's say I found the mean was 4.5. I mean, especially with these numbers, I mean, how close is 4.5 to the minimum? 3.5. How far away is it from the maximum? 5.5. It's not splitting my distribution in half. Remember, the mean and the median are the same for a uniformly distributed variable, so it should be smack dab in the middle or equally as far away from the minimum as it is from the maximum. Okay. Any questions on this one before we keep moving? Oops. Okay. I think I might have wrote these backward, like maximum plus minimum, minimum plus maximum. Doesn't matter. We're just looking for that middle value. Okay. So, kind of a reminder, we got the height of my distribution is 1 over the range, right? Or 1 over the maximum minus the minimum. If I then want to know, well, what's the probability I see this variable take on a value in between any two values, right? Starting with A, ending with B. How can I find that probability? Well, we said we could just think about this as, and I should probably write what the actual mean was, not the wrong one here. If I wanted to find the range I was in between two values, all I'm really doing, we said, was looking for the area of a rectangle, right? What's my height? 1 over maximum minus minimum. What's the width or length of my interval? A to B, so B minus A. Or we said we had this formula that we could just plug those values in. We kind of think about here. This is my maximum. This is my minimum. So if I had an example like this, right, I wanted to find the probability I was in between what? Well, we've got the same setup, same demand. But now I have, okay, what if the movie theater makes 9.5 pounds of popcorn? What's the probability they didn't make enough? Well, the only way that they didn't make enough, or they have angry customers, I guess I phrase it here, is if demand actually ends up being somewhere in between 9.5 and 10. Now that's the only way they won't have made enough, right? They haven't supplied enough to meet demand. So my beginning and my end of my interval would be 9.5 and 10, right? So anytime you could be asked, what's the probability you see this uniformly distributed random variable be above a certain value? Well, you know where it would start then, but where does it stop? Well, it would have to stop at its maximum, right? So your interval stops at the maximum if you ever want to find the probability of being above a certain value. Let's say I instead, and I'll come back to this here in just a second. Let's say I instead wanted to know what's the probability if they make 1.5 pounds, what's the probability they actually, will have enough to meet demand, right? Well, if I want to know what's the probability demand is below 1.5, it would have to start at the minimum and end at the maximum. Sorry, end at the maximum. Start at the minimum, end at whatever that kind of value you would have to be the maximum of that interval you're interested in. Okay. So I've got two intervals here. I'm going to go ahead and try to find the probability of both. So I'm just finding the area of a rectangle here. What would the height of that rectangle be? Give it to me as a fraction.
1/9.
Yeah, 1/9, right? How'd you do that? Well, 1/, the maximum minus the minimum, or 1/9. Okay. So what's the probability I see demand be somewhere in between 9.5 and 10? When I think about this as a rectangle, that's just 0.5 times 1/9 or 1/18. I don't know what off the top of my head what that works out to be, but 1/18, all right? So that's what we have. Now, what if I had done it kind of just using this formula? Well, I just plug in my value. So my A and B are 10 and 9.5. B and C are my maximum, my minimum are 10 and 1. If I put this in my calculator, I also find out that would give me that same value of 1/18. Okay. Any questions here? Because I'm going to throw in some other stuff. Questions over this? Okay. So, didn't really hammer this probably enough earlier, but if you were kind of listening, maybe picked it up. I actually probably don't even have to use this formula again. And hopefully I should know what's the probability I see demand be in between 1 and 1.5. What should that be? 1/18. Why?
Same as
It's an equally sized length interval. The whole idea of the uniform, remember I started drawing out the intervals of length 1 and showed like, yeah, every single one would have the exact same probability of occurring. Right? So here, if I find the probability of an interval of length 0.5, I can find the interval of length 0.5 for any other values in this range, right? The probability it's in between 4.5 and 5, 1/18. The probability it's in between 7 and 7.5, 1/18, right? And I can kind of exploit that and save myself some time. You know, maybe I ask you, well, what's the probability that we see demand be below 1.5 or above 9.5? So I'm looking for both of those areas, but once I find one, I automatically would know the other. And I can prove this to myself if I just go ahead and think about once again, what's the height of this rectangle? 1/9. What's the length or the width? 0.5. Ends up being 1/18 as well. Okay. So we can kind of exploit this fact that every equally sized length interval has the same probability if it's uniformly distributed. Okay. Any questions on that before we keep going? You could, sorry, I jumped the gun. I should give a little more time. Any questions there? So I can actually do some other things as well. This might get a little tricky. Let's say I want to know the probability I'm in between 5.5 and 7.5. Right? Well, how could I find that probability using what I already found over here? If I know the interval of length 5 has a probability of occurring of 4/18, an interval of length, what, 2 would have a probability of occurring of give myself a little more room so I can calculate this to you. If I've got an interval of length 2, let's say I instead say, okay, wait, what if it was just an interval of length 0.5, like I found earlier? So if I went from 5.5 to 6, I know that would have a probability of occurring of 1/18, right? The interval of length 0.5, right? 5.5 to 6, so it should have the exact same probability. What if I then go to, I'll write them up here just so we can kind of keep it confusing. What if I go from 6 to 6.5? What would the probability of this area be? Same length, so 1/18. What about 6.5 to 7, and then 7 to 7.5? Both are intervals of length 0.5. So I know that I just take that interval of length 2. If I could break it up into these areas of 0.5 that I already calculated, each one should have that exact same probability. Or if I know the interval of length 0.5 is 1/18, how many times would 0.5 fit into an interval of 2? 4 times. So I could have just multiplied it by 4, right? Or I could have thought about it as breaking it down into kind of those 4 equally sized length intervals of the one that I already found, right? So you can kind of use some tricks like that. I'm not gonna, you don't necessarily have to always do this. You could recalculate it. You've got your new starting and stop, start and stop value. You could go through, find the area of just that rectangle, that'd be fine. But once you find the probability of one interval for a uniformly distributed variable, it's very easy to scale it to other intervals that are smaller or wider or more narrow. Okay. Any questions on that idea? Pushing that one a little bit further than I usually do. All right, so, whoops, we kind of went through this one. I guess 1/18 is 0.05 cent, right? Rounded. So let me give you guys a little bit of time to work on this next one. And if you remember something I said earlier, it might make this one a little bit easier. You can go through, use this formula, try to find the probability of the interval that we're now going to look at, which is, let's assume we have the same setup, but that the movie theater makes 9.5 pounds of popcorn and they exactly match demand. So what's the probability if they make 9.5 that they made exactly the right amount? So the probability of our interval would stop and start at 9.5, right? We want to know what's the probability that demand is actually 9.5 pounds, right? So I said something earlier, setting up the whole idea of any continuous random variable, that if we're wanting to find the probability of any one value, I said it was equal to something. That's what we're doing here. What's the probability that we see this random variable x take on one specific value, 9.5? Give you a little bit of time to kind of try to recall what we said earlier, and then we'll kind of keep moving. You could also try to kind of use that formula, thinking about your interval is really starting and stopping at the same value, 9.5. You use that formula, that might kind of help remind you of what we were talking about earlier. All right. You haven't gotten an answer. Take your best guess here. They had 32 of us earlier. Just make sure you get a recorded response. One more person. All right, I'm gonna close it out. So what should this probability express as a percentage be? 0, right? We said that way earlier, right? That the probability of any one specific value. How many values are between 1 and 10? If it's truly continuous, an infinite number. So we said the probability of any one value would be 1 over infinity, which is just 0. You can prove this to yourself if you plug the start and stop, right? I'm looking for the probability that it's exactly 9.5. So if I think about, if I have this, and it goes from 1 to 10, and I want to know what's the probability that exactly 9.5 pounds is a demand. Well, it starts and stops at the same value, right? So when I go plug this in to that probability density function, or what gave me the probability of seeing, x take on a value between a certain interval, well, that interval is of length 0. 0 over any range would always be 0. So we get kind of this weird outcome, right? And then even the probability density function kind of supports what I was saying earlier, right? Even if we don't remember it, we try plugging in that we're looking for one specific value. Our interval starts and stops at the same point. We get a probability that occurs of 0. Now, what if I had just to kind of prove the point, I can't find the probability of 9.5, right? But I could actually find the probability of 9 0.50001, right? Because then I would have some, it's a small interval, but it is still some length, right? It's not a length of 0 anymore. I would still have a very small probability, but it would be some number over 9, right? So even if I made the interval really, really small, I can always find the probability over an interval. I just can't find the probability of one specific value, okay? Any questions over this idea? I keep moving. Okay. 10 minutes. How do I want to do this? We'll introduce this idea. So that's our uniform distribution. We're going to move away from that now. I'm going to introduce what we're going to really hammer for like the next couple of weeks, which is the normal distribution. Okay? So we want to think about the normal distribution, sometimes called a bell curve, or I think it was also the guy that came up with it. I can't remember his name now. And his last name was Gauss. So sometimes it's called the Gaussian distribution, but in general, I always refer to it as a normal distribution. It just looks like a bell, right? That's kind of one of the reasons why it's called a bell curve. You can think about it's also symmetric, just like the uniform. It's a symmetric distribution. So that mean should be exactly the same as the median and exactly splits my data in half, right? This distribution should fold on top of itself. But we can't find the probability of any one specific value, and we could do the integration so that if, like the uniform, I was interested in finding the probability that this random variable x takes on a value in between a and b, right? I've got my interval. I could find that probability by integrating this function, and we'll look at that in the next class. It's a nasty function, but I could do that and find that probability I'm in between a and b by just finding the area under the curve in between those two values. Problem is, integration is not very fun. The equation itself is pretty hard to integrate. And so we're going to rely on the fact that people have already done this for us, but they can't do it for every single interval. What they've done is integrated from any value we might be interested in for x, and they found the cumulative probability. So what they essentially did was find the probability that we see this random variable x take on the value of a here, or anything below it, right? A cumulative probability. Okay? So we'll have this table, that z table is essentially going to be giving us those cumulative probabilities for any different value for x. Now, talk a little bit more, we're going to have to do some transformation to this, but for now, you can think about that table as representing, we're interested in, what's the probability I see some value for x or anything below it. I can get that probability from the table. I can get that area under the curve without doing the integration. Okay. Questions? So when x is pretty small, that probability should be getting closer. Sorry, I said x. Yeah, when x is a small value, it should be getting closer and closer to 0. For really high values of x, if I want the cumulative probability, that should be really, really close to, well, what's the total area under the curve? 1, right? If I looked at the highest possible value I could ever see for x and said, well, what's the cumulative probability? Like think about like income. And I said, well, what's the probability somebody makes less than $5 billion a year? Well, that probability is 1, right? Well, I don't know. Maybe some of these billionaires are making more than that annually, but you get the idea. Which is chosen an obnoxiously high value, the area to the left or the area under that curve should be really, really close to 1. Okay. So we'll start writing, we could write that if I wanted the probability of seeing a or anything below it, we'll use that cumulative density function. We'll write as actual f of a. Okay? So there's going to be some density function that gives us this line. We'll kind of call that small f of x, right? This big f of x, right? That's going to represent our cumulative probability, or the probability I see x as the value or anything below it. In this case, I'm not using x. I'm kind of using this value of a. I'm just using different. I could then also think about, well, what if I wanted to find the probability of being greater than b, right? Well, this is like the problem. This is kind of like when we're using the binomial in Excel. If you ever wanted the probability of being above a certain value, there was no function for that, you have to do 1 minus. Well, here, if I can have a cumulative density function, that gives me the probability that I see B or anything below it. Well, then if I want the probability of seeing B or anything above it, that's just 1 minus that cumulative density, right? I can always use that Z table to find the probability of being below a certain value. So if I'm ever interested in finding the probability of being above that value, just go to that table, find the probability of being below it, subtract it from 1. We're using that complement rule. All right, we won't like explicitly say that, but that's essentially what we're doing. And the visual is kind of, nice because if the area under the curve is 1, well, let's say I find the cumulative probability, the probability of less than B is 0.6, what would the probability of being above B have to be? 0.4. It's the only, I'm either on one side or the other, right? So this is kind of how we can use this cumulative probability to find the probability of being below or above a certain value. And then I have one more, which is, and this is, I think, trips some people up a little bit once we get to further into the normal distribution. Well, let's say I want the probability of being between two values, right? So I've got this guy here, and I want the probability of being between those. How could I use my cumulative density function to find that? And the cumulative density is always the probability of seeing a certain value or anything below it. So if I want the probability in between these two values, what could I do? So if I use the cumulative density function, and I find the probability of seeing A or anything below that, I then use my cumulative density function to find the probability I see B or anything below that, or the area to the left. How could I use those two values to then find, well, what's in between them? I take this green shaded area. What do I want to get rid of? That red shaded area. Remember what I originally wanted to get between A and B, or this black shaded area. So if I take the cumulative probability of B, and I subtract out that red area, or the cumulative probability of A, that should give me the probability I'm in between those two values. Right? So we can use this cumulative density function to find the probability of being above a certain value, below a certain value, and we'll also then use it to find the probability we're in between two values. Right? So eventually, this will have the power of like, if I chose someone at random, what's the probability? I'll use height because I know human height is like pretty normally distributed. I could find the probability that if I chose someone at random, what's the probability they're below 6 feet tall? What's the probability they're above 5 feet tall? Then what's the probability they're in between 5 and 6 feet tall if I chose someone at random? We can kind of start answering questions like that. Maybe the human height one doesn't seems a little trivial. You can think about, if I chose a person at random, what's the probability their income is in between these values, probably that their I don't know, age is in between two values. So we'll start looking at variables that are normally distributed next class. We'll also then talk about how do we take a normal distribution, convert it into what we call z-scores, and then be able to use that z or that standard normal table. Okay. All right. I will see you guys on Wednesday. I will have the exams and hand them back at the beginning of class.